Hi, I am Sala. In this video, we'll discuss discretization of linear state space processes excited by white noise, and we'll concentrate on what's called Van Loen's formula. In basic computer control courses, we know that if a process has a zero-order hold in front of it, then it has an exact discretization, and it can be computed with matrix exponentials. So what about noise input? The evolution of the variance is governed by a variance equation, and it has a solution with integrals of exponentials. And in this video, we'll discuss what's called Van Loen's formula to obtain the accumulation of variance in one sampling period without the need to carry out integrals. We'll only need matrix exponentials. Our process will be this linear process excited by white noise, which can be formally interpreted in Ito's sense as this thing, where dWv is the infinitesimal increment of the linear process, which has this variance, identity differential of time, if it's the standardized normal one, or it may have this variance if it is a white noise with power spectral density different to 1. The issue is that if initial conditions are a normal distribution, then the evolution in all future time will be also a normal distribution, and that's called a Gaussian process. And if we know its mean and its variance matrix, then we can completely determine the probability distribution, and it's shown elsewhere that the evolution in time of the mean verifies this differential equation, and the evolution of variance verifies this differential equation, where P is actually a matrix. The mean is a vector, but the variance is a matrix. Anyway, these are linear ordinary differential equations that can be solved with exponentials and integrals of exponentials. In the variance equation, this W is a known variance or power spectral density parameter obtained multiplying left F, right F transposed, the power spectral density of the exciting noise. If we wish to discretize this process, then we need to integrate the mean and variance equations during a sampling period, capital T. Let us discuss briefly now the mean equation. The goal will be discussing variance later on. The mean equation is easy, it's just simulating the process without noise. So if we have a zero-order hold because we want to discretize for computer control, we need just adding that the input is constant in the middle of a sampling period. The final discretization of the mean equation is this one, and ADBD can be computed in two equivalent ways. We can either go to textbook solutions of ordinary differential equations. We'll have something like this, in which this matrix exponential will be the discretized A matrix here, and this integral of a matrix exponential will be this B discretized matrix. There is no noise here because we are only considering the evolution of the mean, the expected value. Well, numerically, this integral of a matrix exponential is kind of dirty. We could do it symbolically, but okay, this expression in the middle of the slide is a convenient way of avoiding the computation of this integral. Indeed, if we add as many rows of zeros in here as deterministic inputs, then the matrix exponential of this AB00 times sampling period gives me AD and BD over there, which of course are coincident with these ones. Details are not in the scope of this video for the sake of brevity. What we wish now is to derive similar expressions for the variance accumulation. Let's go. In other materials, we can prove that the solution of the variance equation, the solution of this matrix differential equation, is the one highlighted here. If we are discretizing, we just need to replace lowercase t by uppercase t sampling period. So we'll get the A matrix and a transposed matrix discretized, the same as in here, but we have this new stuff here, which is a double integral of exponentials. In here we had a simple integral of exponentials, and padding with zeros, we got a way to avoid computing that integral. And in here we have the double integral, so is there any bigger matrix so that its exponential can help me compute this WD? The answer is yes, and it's called Van Loon's formula. Of course, once we compute everything, this thing is the variance equation for this discrete time, actually sample data, of course, because it comes from a continuous one. So for this discrete time linear stochastic process. So if we are able to compute this WD, then we will have finished our discretization. How can we compute WD or its limit when capital T tends to infinity, which is called gray mean, stationary variance, interesting in many applications? Well, we can do it in several ways. If A is small, the Matlab's symbolic toolbox can swallow this kind of expression and compute the metric exponential symbolically, so the direct symbolic computation is an option. Then, of course, there are another formulae for some subclasses of systems, either being stable, either being without poles at the origin. We can diagonalize and do exponentials of Jordan forms. I mean, no problem with that. But we have the so-called Van Loon's formula, which is in theory valid for any system, but maybe in some cases it's ill-conditioned. But okay, in reasonable chosen sampling periods and models which are not stiff, I don't want a pole in -1, another pole in -2000. So in reasonable setups, Van Loon's formula gives good results, and then these two commands in Matlab, which compute optimal state estimators in processes with noise, or the dual problem of optimal sample data linear quadratic regulator. Well, in these commands, Matlab uses Van Loon's formula, and so it's worth looking a bit in the details to see why and how Matlab does it. So we'll concentrate on this as the main goal of this video. Let's delve into the details. We'll start by defining this capital theta matrix and realizing that theta squared is this thing, and if you go on multiplying, you will see that theta cube, fourth, and all powers are upper triangular. So we have this 0 in all powers of theta. Then the matrix exponential of theta t will also be upper triangular, because this is Taylor series identity plus theta t, theta squared, t squared over 2 factorial, and further elements, but it's a sum of upper triangular matrices. So this matrix exponential will have this form, being f1, f2, and g, some matrices with lots of exponentials or whatever. In fact, we will compute them in next slide. For the moment being, the only thing we know is that this will be 0, and that for t equals 0, as the exponential of the 0 matrix is identity, in t equals 0, this will be identity, identity, and 0. So we know this kind of initial conditions. Van Loon realized that actually it's not too difficult to compute what this f1, f2, and g will be. Why? Well, because if we take the time derivatives of that matrix, which is of course the time derivative of this matrix exponential fulfills this thing. You know, the exponent goes down. So thanks to this nice property of matrix exponentials, this is capital theta, this is the exponential we wish to compute. We still don't know what we will have inside, but carrying out such product, we'll get this thing. So if we go element by element, we can see that the time derivative of f1 is this thing. I will write it here. The time derivative of f2 is this thing. I copied it down here. And the time derivative of g is this thing. Again, I copy it down there for further use. So the conclusion is that as everything related with matrix exponentials, f1, f2, and g verify these differential equations, first order, and we know that the solutions of differential equations are matrix exponentials. Indeed, the solution of this first equation is the exponential of minus a times the initial condition, and we know that f1 was the identity. So as this is identity, we know what f1 is. Similarly, the solution of this, and this is somehow the same equation as the first one with f1, but just transposing things, then it's easy to check that it's the initial condition multiplied from the left instead of from the right by the exponential of this matrix. So this is f2. Indeed, if we take time derivative and we use this property of the matrix exponential, then we see that the time derivative of this thing just multiplies at the right by a transposed, which is what we wish to obtain. So this is the solution, and again, as f2 was identity as initial condition, this is 1, and we readily solved for f2. Next, what happens with g? In this case, this is like a first order system with a known input. Indeed, once I know the solution of f2, I can plug it here so that its solution will be a minor variation of this kind of exponentials. But okay, in here I will have u of tau, but okay, this is textbook stuff of first order linear equations. So this is the solution g of t, the exponential of this matrix. Here we have it, times the initial condition, that would be the, let's say, free response, and the forced response will be this element here. Luckily, as initially g was 0, then this is 0, so we can just forget about this term. So this is g of t, and the only remaining thing is, of course, replacing in f2 the solution here. Doing that replacement, then we get the final expression of g of t. So this was f1, this was f2, and this was g. Now, Van Loon realized that, bingo, this is what we wish to compute. Here we have it. So the only remaining step is multiplying by the exponential of plus at, so that this cancel out. Indeed, if I multiply that negative a exponential by positive a exponential, then product of exponentials is the exponential of the sum of a minus a, so this is exponential of 0, this is just 1, identity matrix. So if I multiply g by this exponential, I'm done, finished. And the exponential of positive a is just the transposed of f2. f2 transposed is what I need. So if I multiply f2 transposed g, then everything works correctly, and I obtain the discretization of the accumulation of white noise that I was looking for. So that's the main result of this video. This is the so-called Van Loon's formula. Let us summarize and conclude. We proved that this integral in discretized variance equations can be computed by forming this matrix and carry out its metric exponential. So it's one line, exp_m. And then taking the rightmost columns of that metric exponential, the transposed of the lower block times the upper right block, is the short exact discretization of the effect of noise. This is good, and this is what Matlab does. And it works if sampling period is small, because, okay, we have both positive and negative exponentials, both stable and unstable poles make elements in this matrix grow wildly in some parts of the matrix and quickly diminish to zero in some other parts of the matrix, so conditioning is progressively worse as capital T increases. But okay, for reasonable sampling periods in computer control, as I said, this is the default implementation in Matlab. Good, I'm finishing here. Thanks for watching.